Hello and welcome to today's webinar. This is Mark Plantier of Enercon Industries, and we'd like to thank you for attending today's presentation on the top 3 strategies to improve your adhesive bonding operations. Please note the webinar is being recorded, and you will be able to access both the recording and presentation slides once they are available online, usually within 24 hours. We will send you an email. If you have any questions during the webinar, please use the GoToWebinar question tool. You may submit a question at any time during the presentation. We'll reserve time at the end to answer as many questions as we can. Today, we're fortunate to have 2 presenters who are recognized as experts in their respective fields. Lucas Dillingham is BTG Labs Vice President of Sales. His experience includes over 10 years of implementing inspection technology, developing process control plans, and solving production challenges related to surfaces. Wilson Lee is Enercon's Business Development Director. Wilson has extensive experience in surface treating applications over a wide variety of industries. He works with Enercon customers on developing plasma and flame technology solutions to solve their surface treating challenges. Wilson earned an electrical engineering degree and an MBA from Clemson University. For those of you not familiar with BTG Labs, the company works with manufacturers on improving quality, consistency, and repeatability of their adhesion operations through education, consultation, and the implementation of diagnostic devices to create a more predictable and scientific approach to successful bonding. Enercon is a global supplier of innovative surface treating technologies, including flame, atmospheric plasma, and corona, which are designed to improve adhesion of adhesives, inks, paints, and coatings. The multinational company supports its customers through an international network of operating centers. Today's presentation will provide you with insights that will empower you to make improvements to your operations. Our presenters will begin by sharing insights on conceptual strategies and then dive in on how these concepts are being applied to improve adhesion operations with a specific emphasis on surface preparation techniques and diagnostics. At the end of the webinar, we will reserve time to respond to your questions. With that, I'll hand it over to Lucas to start us off with 3 conceptual operation strategies.
Thanks, Mark. Lucas Dillingham here, guys. Thank you very much for attending. Those who are online, I do want to stress, if you guys have a question, something that we say kind of sparks a thought, throw it into the chat box. We will try to address them all at the end. Love to try to keep these as interactive as possible. So to get started, we're going to talk about some kind of high-level concepts and then start drilling down into some of the applications that are near and dear to our hearts. So there are some major goals that we're trying to do, or I should say we're trying to accomplish as manufacturers, all right? One of them is reducing operational assembly and complexity. We want less parts, all right? And things like adhesives and sealants and coatings allow us to achieve this, right? If you look at our nice little Henkel Covestro white paper generated image here of this battery cell, I don't see a single screw. I don't see a single fastener. I don't see any threads that I've had to cut. I don't see anything that I've had to machine. Other than maybe the nickel battery cell itself. But we really want to reduce operational assembly complexity. This leads to higher quality. It leads to cheaper manufacturing cost. It may require some more design time, all right? But this is extremely important. Additionally, things that we want to do is we want to reduce manual operations, right? Along with reducing assembly complexity and really the number of parts that we're putting into a product, right? If you think about how many parts are in an electric car versus a traditional internal combustion car, I mean, it's on order of magnitudes less. We want to do the exact same thing for how we're actually putting these things together, right? We want to reduce the amount of people, the amount of human beings really involved in building the product. This helps us reduce not only cost, but just variability, right? I mean, we all see the world with slightly different eyes. And we all do things a little bit differently, right? Whether we want to or not. So we really want to do this. So we need to look at strategies, materials, assembly operations, surface preparation techniques that allow us to reduce kind of the manual factor, right? The manual input. And then thirdly, we really need to begin, and this is a huge trend and a huge thing that people are really talking about. We need to be able to start working on data, right? Not gut feeling or tribal knowledge or what we did on the last program. We need to start using data to make decisions. You know, does MEK really clean better than acetone, right? A lot of people, or better than alcohol? Maybe, right? A lot of people would say yes, but where's the data that really proves that and supports that, right? We want to use hard known information to challenge our assumptions and make our decisions moving forward, right? So all of those things, right? Reducing operational complexity, reducing the manual operation, using data instead of tribal knowledge to make decisions. These are the things that really are going to help us take advantage of new high performance materials and technologies that exist, right? We need to move to higher strength. We need to move to lighter weight. The customer has, I'll say, much improved standards on reliability and predictability. I don't know about you guys, but I don't think, I know a lot of folks still on their iPhone 6 and iPhone 7 until the 5G network is gonna force them to upgrade. We just have higher expectations. And not only that, we've got to produce these things at lower cost, all right? And so these new materials and technologies that exist, they really require improved manufacturing techniques, all right? We need to have flexibility to adopt, I'll just say, surface critical tech, so advanced coatings, adhesives, right? Using adhesives is really the only way that we reduce, certainly structural assembly, I should say, reduce the amount of parts that go into structural assembly. We've got to have better quantification and documentation of what's going on in this region. All right. There's a huge need to really understand and manage surface properties in a big way, right? If I'm going to start using adhesives in a major way, all of a sudden we've got some, really 3 critical inputs that are going to control that, all right? And this is a really great mental model for how we think about adhesion systems, right? And an adhesion system, I mean, it's not just like epoxy, right? It's a sealant, it's ink, it's a paint, it's a PSA, right? It's tape, right? Depending on what I'm going to use. But there's really 3 key inputs that if we control, we're going to get a reliable and repeatable output. This thing is going to perform the way it's designed. And the first one of those is the properties of the chemistry we're going to apply to the surface, the adhesive itself. All right, and your Henkels, your H.B. Fullers of the world, they do a very good job controlling their adhesives on a batch-to-batch basis, right? They're literally controlling monomer ratios as they're producing this stuff. And there's batch and lot and manufacturing information that exists with these. The second thing is the surface condition, right? It's the surface that we're going to apply that adhesive to, all right? And I'm going to get into really what this means from a technical standpoint, but this is a very important point. The third thing is the adhesive application, all right? And that simply means the bead width, the cure profiles, the ambient temperature, the fixturing, the pressure, all the things that physically need to come together to get that adhesive onto the surface and make sure it cures up appropriately. And manufacturers typically do steps 1 and step 3 pretty darn well, all right? But what we find in almost 90% of adhesion failure cases, what's happened is something has changed with the surface. Something's changed. Contamination, handling, something changed with the manual cleaning or surface preparation action. And so that's what we're going to focus on today, right, is surfaces.
Hey, Lucas, this is Wilson. Sorry to interrupt. Go back to that last slide for just a second, because this is a question that I get that I'm sure you get all the time too. When you bond 2 things together, how do you know that you've got a good bond without breaking it?
Yeah, I mean, it's a really good question, Wilson. So this is actually how we get to that predictability, right? If we have the critical information of these 3 inputs, we are going to be able to predict performance. All right. Now, in the development and design phase, we are always going to do some functional, adhesion testing, right? We are going to break some things apart, but by controlling these 3 inputs, certainly in a production scenario, we can greatly reduce, if not totally eliminate, destructive testing, right? Because these are the three things that got to come together, right? It's the adhesive, the top few molecular layers of that substrate, and how we're putting the adhesive down onto that part. That's a good question. So let's understand and dig into kind of what a surface is, right? And what matters and what do we need to measure around surfaces to get that reliability and predictability out of adhesion. So there's really basically, we're going to look at 2 material types, or I should say 2 material classifications. We'll look at metals, all right, which Metal, ceramics, glasses kind of have some similar behaviors, and then we'll also look at polymers. So what this diagram is showing here on the lowest level is a metal surface that has been freshly created, all right, brand new. You can think of something that's been laser ablated, for example, or just totally ripped apart. And when you create that surface through that operation, you literally fracture molecules. You rip a portion of the surface apart. And when you do that, you've got all these unsatisfied molecular bonds, all right? And what happens immediately after that is you get an oxide. And I'm literally, and especially in atmosphere, I literally mean immediately, you start getting an oxide, all right? Then you start getting a little bit of water vapor that it starts attaching itself to these reactive sites on your surface. And then as that material sits out there as a very high energy, very reactive material, you start getting contamination just through adsorption in the atmosphere, right? Hydrocarbons, water vapor. Hopefully nobody's touching this with their bare hands. And every time you got a molecule that attaches itself to that surface, you lose a reactive site. You lose some of the reactivity or the energy, right? The jargon, if you Google this, will be the surface energy of that material to do work when you put a liquid adhesive or sealant or coating in contact with it, right? So all materials go through this process. I should say all metal materials go through this process. It's important to understand. Adhesives, functionally, the reason we need to clean, right, or activate is we've got to deal with that very top layer of stuff that's sitting there on that surface. All right, we've got to either change it or remove it so that we've got some reactivity there for our adhesive to interact with. And it's really important to understand the region that adhesives really care about. If I can see a fingerprint on a surface, that's about 10,000 molecules thick. Adhesion is really happening in the region of 2 to 20 molecules thick. It's invisible, right? I can look at two shiny metal parts. One could bond incredibly well, and one won't bond at all. And so that's a very important thing here, right? When we're talking about what do we need to be sensitive to? Let's take a look at polymers because they look pretty different. All right, so a polymer surface, after I've molded it, it's basically just spaghetti. All right, it's extremely long carbon chains. All right, there aren't really any broken bonds. There's really nothing to even interact with. All right, and so what we've got to do with polymers typically is we've got to activate them. We've got to chemically change that surface so that we've actually got some reactivity to stick something to it. Right, and Wilson is going to get into this in more depth. But instead of going from kind of a natively high energy surface like a metal or ceramic or glass that contaminates through processing and handling and being in the environment, we then got to remove that. Polymers are different. They start kind of in a lower energy state, and you've got to manipulate them to get them to a higher energy state to be able to start sticking things to it. All right. And that brings me to my next point is like, what are just the overarching goals of surface prep? Like, what are we really trying to accomplish? Well, when we're looking at our workflow or manufacturing process, really the goals here, we got to remove contaminants from upstream processes, and they look different. Like what we define as a contaminant looks different based on what we're working with. If we got a polymer, a lot of times we're trying to deal with contaminants from molding, right? Usually many times we're applying mold releases to be able to get that plastic part out of the mold, but that's that we're purposely putting that on so things don't stick, and now we've got to go and take this part and stick something to it. So we got to deal with that. When we're talking about metal parts, many times we're talking about machining. Could be stamping, could be die casting, but many times we're talking about machining, and we've got lubricants to deal with. If it's gone through a parts washer to remove particulate and remove chips, then if we've got a poor rinse process, then we're going to have soaps and whatever's dragged out of that washer. All right, so we have those to deal with. And then there's the material storage and handling, right? You touch these, you bag them, you ship them. All of those are areas where contamination or basically bad things can happen. We need to create a chemically reactive surface. All right, adhesion depends on surface chemistry. on chemistry in general, so it's got to be chemically reactive. And then we also have to create a chemically uniform surface. We really care about the consistency of the surface that we are creating. That's why many manufacturers will find that when they manually clean something, they literally have more scrap and warranty claims than when they automatically clean something, like say by using a plasma on the end of a robot. All right, so it's the uniformity, the reactivity, and the ability to remove some contamination are all kind of the overarching goals of being able to prep surfaces well. Now, if we're prepping them well, we got to measure them well. Okay, and if we go to the next slide here, there's a couple technologies that are available for shop floor use that allow us to get some information about the surface chemistry of our substrates. And remember, I was talking about how we really care about the top 2 to 20 molecular layers, right? So we got to have tools here that are sensitive to composition, structure, and really the amount of a very, very thin layer on a particular surface. All right, there's handheld FTIRs out there. There are XRFs out there which aren't as surface sensitive, but most people really are trying to institute wetting measurements in some capacity. All right, so we'll focus on those here. You can go to the next one there, Mark. Thank you. So in general, and I'm sure you guys are familiar with some of these, folks have been trying to use wetting behavior tests for a long time, right? Just looking at how does a liquid interact with the solid substrate to try to get an idea of what's going on. And in general, and folks still are doing this to a large degree. Water break check, water break testing is really common in painting, for example. In the aerospace industry, this is where we spray a part down with like DI water, and we wait a couple seconds and we watch, does it sheet or does it beat up? We try to get kind of a subjective binary go, no go. Dyeing inks are another common technique where we take an ink of a particular surface tension. They're usually a known surface tension unless they've expired, which happens all too often. You paint the surface with it, you watch it for 5 seconds, and you try to say, hey, is this a 44 or 38? All right, they're subjective, they're destructive, they're really not a 21st century solution. They're not even a data-driven solution. From a laboratory perspective, people have been doing contact angle measurements for a very long time, right? 90 years. Those are where we put a liquid droplet on a surface and we measure the angle that the perimeter of the droplet makes with the surface. All right, and they're sensitive. It's really a great technique, but the problem is that it's slow. You need a trained operator. It's laboratory only. You can't measure geometry. You have issues with roughness. So you're not really measuring real parts. You're measuring flat samples. And then that brings us to what we provide to many of our customers, and that's really a full platform to do measurements on the factory floor in a variety of capacities, from full portable to fully inline. So let's look at minimizing variables in surface prep. All right, you guys heard kind of in my goals of surface preparation, like the overarching goals, what do we need to do to deal with a part in our manufacturing workflow? Well, we actually call these points in time critical control points. All right, these are all the areas in a manufacturing workflow or in a supply chain where surfaces can change, either negatively or positively. And they are the areas where, when we get called in to go solve an adhesion problem, these are the areas where we always find stuff, every single time. All right, and it's really broken down by the incoming material, right? What are we feeding our process? And that could be at a supplier, that could be just simply upstream. Maybe you got the molding operation next door, whatever it may be. There's variables there. We've got the storage and inventory of our material, right? How it's stored, where it's stored, how it's shipped, how long it's been since it's been produced. All of these matter, right? The longer you store and inventory a thing, the more opportunities there are for contamination to occur or aging to occur. And then we've got a cleaning process. Many times we'll have a surface activation process, and then we'll get to our final step where we're actually applying our adhesive or ink or sealant. So Wilson is actually going to dig in here to our surface activation steps and give you guys a little bit of primer on that. So go ahead, Wilson.
All right, thanks, Lucas. So yeah, what we're going to talk about now is the third and fourth steps that Lucas just mentioned, cleaning and surface activation. So there are a lot of options out there. Again, their primers have been around. Wet chemistry, as we usually call them, have been there for years. Lucas has already alluded to the fact that these are usually hand processes and or human processes, and they're inconsistent by nature. They do work, but they're harder to control. Chemical etching can be done. It's expensive and permanent, but it also creates hazardous waste and hazardous material that you have to do something with. There are mechanical preparations that will work very well. Maybe that's a sandblasting or something, but then, excuse me, you still have to clean the part. You still have to get it ready for the next activation section. There are vacuum plasmas, which work very well. The issue there is usually they're a batch process. There's a couple of inline vacuum plasmas, but not very many. And so the batch process takes time, so you have to have large chambers for larger parts. And it takes time. If larger chambers, it's going to take a longer time to reduce that down to a vacuum pressure, and then put in the process gas, and then you ramp it back up. So the larger the chamber, the longer the cycle time. And then you have what we use at Enercon is the atmospheric plasma and flame. These can be inline, continuous, and can be very economic on a day-to-day basis. And there's very little cost involved in actually using these technologies. So the benefits of inline plasma and flame treating. Let's go over that for a little bit. Who is using plasma and why? It would be very hard to find an industry at this point that does not use plasma in some form or fashion. A lot of companies are starting to recognize, as Lucas mentioned before, that the quality of the surface is extremely important if you're going to have a continuous process that is repeatable. So, I mean, if you're using adhesives or you're printing or you're potting something, surface activation is critical on those. The automotive industry is certainly a big plasma user, window and door, wire and cable, but this is just a cross section of the number of industries that use our processes. And the reason they do this is, first, we're creating stronger bonds. Again, back with using the correct adhesive and using the correct processes and having the correct surface, all of those things lead to stronger bonds. Whether you're talking about an adhesive bond or a printing or a coating or a painting, it doesn't matter. You're getting a better bond. You're reducing material cost, whether that's within waste or maybe just in the use of the amount of adhesive and coating and potting material that you may need. You're increasing throughput. All of these things are reducing a better quality product, and it's very repeatable. So again, this is what we get asked every day. Usually we get calls from customers who are looking to improve a process that they've probably been doing for a while and have certain issues that they're trying to overcome and looking for better solutions, more modern solutions to help solve those problems. So what does plasma do to the surface? We've done a complete webinar on this, but we'll go through this really quickly. Plasma, really quick, is just the fourth state of matter, solid, liquid, gas, plasma. In a plasma, many times you think of the lightning strike as being plasma, northern lights, southern lights, they're plasma. Most of the universe actually is plasma in its forms. We use plasma to activate the surface, but in there you've got positive and negative ions, you've got free radicals and electrons, and then you've got UV light, which gives the plasma the look of kind of a flame. But all of those things are bouncing around in the plasma field as you are attaching it to the surface, or attacking the surface with it, I should say. So what are the three things that we talk about with plasma? Well, the first thing that it does is clean. Again, cleaning and activation are the two things that we're really worried about here, but we also get a third micro etching component to it as well with the polymers. Cleaning. Organics are relatively easy to clean. They're usually hydrocarbon change, and when you attack it with compressed air, which is going to be hydrogen, oxygen, nitrogen ions, what you're creating is CO2 and water vapor that's coming off the surface. Inorganic impurities are a little more difficult. They take longer to do. Sometimes you can't do it. It just kind of depends on how much of that inorganic material is there. You may have to have a cleaning step prior to the activation step to get those off of there. Also, you can see on the left side, we've got a relatively smooth manufactured surface. And as it goes through the plasma on the right side there, you'll see that it's been micro etched. Now we're talking 5 to maybe 20 nanometers. So this is not something that's visible to the naked eye, but it does increase the usable surface area that you have. And the more surface area you have for bonding, the higher the bond strength. Finally, functionalizing the surface, or activating the surface sometimes it's called. What you're doing is increasing the polar groups on that surface that make it easier to bond to. So you're actually changing the outermost molecular couple of layers and adding functional groups like hydroxyl groups or carboxyl groups if you're talking about flame, and that is what is increasing that surface energy. That's what you're able to measure with BTG surface analysts. You're able to see the increase or the decrease in the surface energy that you have, so that you can know where you're at and know what your product state is before you bond or print or paint or coat. So now here's what we started with. If we have a bad surface, maybe a plastic surface, it's going to have a low surface energy. There may be contamination on the surface that hasn't been cleaned off. If you're dealing with polymers, you may have additives in there that are migrating to the surface. Flame retardants come to mind. All of these things give you limited bonding sites, and we call this a hydrophobic surface. This would be a similar surface to a waxed automobile or a rain-exed windshield. In these cases, the water just beads up and rolls off. And that shows that we have a very low surface energy. After treatment, after cleaning and surface activation, we have a much more hydrophilic surface. We have increased bonding sites. If there are migrating additives that are on the surface, we remove those, and hopefully we've removed all the contamination, and this gives us a better surface with which to bond to. So what are the technologies that we use? We usually go through a lot more information about these, but we're just going to talk really briefly about the 4 different things that we do here at Enercon and what might be best for your application. On the left, we see the blown arc system. Each of those nozzles will do 3.5 inches of treatment. So if you have a dual head system, that'll treat up to 7 inches. It's a little bit slower treatment. We're talking 5 to 15 feet per minute, depending on your application. And it can only be used on non-conductive surfaces. So if you've got a conductive surface like a metal, you can't use a blown arc on that. But if you do have a non-conductive surface, you can treat up to 7 inches wide very easily. It's great for printing. It's great for labeling, just increasing the surface energy of a larger area. Second, there you see the blown ion. That's what most people think of when they think of plasma. It treats about 12 millimeters or about 1/2 inch. Again, it's offered in a single and a dual head version, so we can treat up to about 1 inch wide with one system. It also is a very ion dense, so the amount of ions coming out of that head are significantly higher than the blown arc in a more concentrated area. And what that means is I can go a lot faster. I can treat up to maybe 100, 120 feet a minute, depending on the application. If I put 2 heads in parallel, I can treat much faster than that. The thing to keep in mind about both types of plasma is the amount of ions that are attacking the surface are dependent on 2 variables, and that is speed and distance. So if I want to increase the amount of ions on the surface, I need to either slow down or get a little bit closer. If I want to reduce the treatment a little bit, you can actually over-treat some surfaces. You might want to move a little further away or go a little faster. The third thing we have here is the flame plasma. That was in the video at the beginning. Flame has a lot of advantages over plasma in certain applications. We can make a burner just about any size that you would like. Also, it is great on multi-dimensional surfaces. I just mentioned that flame, you have to be, or excuse me, plasma, we need to control the distance from the surface. Well, flame gives us we do need to control the speed, but the distance from the surface, I've got a little bit of a window there where I'm going to get a good treatment. So that's why you see it used on door panels and dashboards there, because those are very multidimensional. You're going to have a lot of different areas, and the flame plasma gives us about a 4 or 5 inch area where we can get good, consistent treatment without actually controlling the distance from the head or the burner in this case.
You know, Wilson, one thing I want to jump in on, the thing that I like about that actually is it just reduces integration cost, because if you don't have to program for, you know, real tight Z dimension to the part, then you got more room to play. You literally have to spend less time programming.
Yeah, it really does make it a lot easier, and that's why you see this, especially in something like a dashboard. You just can go back and forth. The process time, the cycle time is very, very low, and it's very easy to treat parts. So if you've got a very three-dimensional part and you come to us, we're probably going to start recommending a flame type plasma for that, just because it's easier to make that programming. If I have to program, if you're going to do a lot of coding, let's say of a bunch of different parts, let's say your business is coding different or printing on different materials for different customers, you're going to have a lot of different items that might come through that you have to print on, and they're all going to have to be all have to be done differently. So if you have to program each time, maybe you're doing 1,000 of these today, 500 tomorrow, 200 the next day, you've got to reprogram every time, where Flame gives you the ability to treat those without having to do that. So we can use a conveyor and a flame system to do that. With the 500 on the end, it is a blown ion. From the second picture, it's kind of its grown-up big brother. It is a multi-port design. You can see it's got 6 ports there. Generally, this will treat 50 millimeters, thus the name 500, or about 2 inches. And the advantage that this has is many of our competitors have 2-inch heads, but what they're doing is taking one blown ion head and using a special nozzle and spinning it around to create that 2 inches of area. Now, that is very good on a low temperature material where you can't take too much thermal damage. But if you need to treat a metal or a hard plastic and you need to do it fast, then the blown ion gives you a 3 kilowatt output versus a 500 kilowatt output, and you can go much, much faster. So you're allowing yourself there to treat very fast at a very high width. The next question we get asked all the time is, how long does this last? Now, we're always going to say, and I'm sure Lucas would agree with this, as soon as you treat something, the best time to do something is immediately. And that's because, as he said in one of the first slides, the longer you wait, the more things that can happen, the more variables you're adding to your process. So this is a chart that we came up with. So if you start at a relatively high contact angle over here and you treat on the left-hand side, it's going to drop down to a steady state portion that I've marked at time T. Now, how long is T? T is going to vary with every surface and every different treatment method. So the only really good way to find out what T is to actually test your surface in our lab. We can give you some
environment, Wilson. Let's not forget the environment, because that's you activate a metal and you put it out in by the ocean. it's not going to last too long, right? I mean, that's all those things matter.
Yeah, there's hundreds of things that are going to affect how long that lasts. And he's absolutely right about that. So your environment is definitely going to affect that. The treatment that you use, the material itself. So I mean, just think of a composite. There are so many different resin combinations for composites. Everyone's going to act slightly differently. Then you're going to reach that time T, and then it's going to start to creep up. Generally, you don't ever get to where you started because you have made some molecular changes to the surface, but you still are going to get to a much higher energy level after an amount of time that's usually between sometimes minutes, sometimes days. And one thing that you need to think of is what area that you need to be in. That's what we'll help you with. What if you want a consistent product? Where do you need to be on that curve to make sure that you've got a good bond? Let's say you're storing it perfectly and you're not going to have any outside contamination. There's still a time that it's going to, the treatment's going to last that you need to do. So that's where we've got T1 sitting out there. So we can help you determine that time with different types of testing in our lab and make sure that you get a consistent treatment and a consistent bond. These are some just random lab reports. You can see we have dyne and contact angle there. We're going to concentrate on the contact angle, which is the second column for these. We have polypropylene, which started at a very high contact angle of about 94, 95. After a blown blown ion treatment, it dropped down to 47.83, and then a flame, it did a little bit better, went down to less than 39. You also have polyethylene. We're not going to go through this whole list. This is just so that you can have it when you download the webinar. You've got a much higher contact angle of 114, and you can get down in the 40s or 50s after a blown ion or a flame treatment. So one of the things you do see here is that different materials react better to different chemistries that are added to the surface. Again, plasma is going to put hydroxyl groups on the surface, and flame is going to put carboxyl groups on the surface. And in some situations, that blown ion is going to work a little bit better. Some situations, the flame is going to work a little bit better.
Well, you know, Wilson, what we would say from our side too is not every material and process needs the exact same, I'll just say metric to determine whether it's good or bad. And so like, you know, as an example, you know, many legacy programs or manufacturers who've been making a particular type of product for a long time, they may have a dyne ink specification and might say, hey, get below 36, right? Or get above X value, and just as a blanket thing. And that really leaves a lot of optimization on the table, because is that really the right number, or did that just get translated over from the previous program? Many times, if you can dial it in with some more accuracy and objectivity, you can find like, okay, hey, my process always runs between X and Y in this range. That process over there with that material, I can actually get away with, you know, a higher speed, or you know, just better throughput, because I don't need to quite get that surface to that level. So it's just, you know, as much as people like want that answer to say like, tell me what good is, the true engineering answer is it depends. Let's figure it out for you.
Yeah, I just had that conversation with a customer a couple of weeks ago, and there was a bunch of engineers in the room, and I said, listen, I know we're all engineers and we all like to have this happens and this happens and this happens. Well, unfortunately, surface energy sometimes is not that easy. And so it's a difficult conversation to have, especially with engineers who want, you know, data that they can count on. But you're right, these things change. There's a lot of variables in play there that you have to take into account. So here's just a couple of, we're going to get into some, you know, different tests here. We had a control group here, and we showed that both flammable and ion in this case gave us a greater strength factor of about 3.5. I think Lucas in a minute is going to start talking about the validity of some of these tests and make sure you're using the right test for the right application. This happened to be a polyethylene with a UV cured adhesive. On the next slide, we're looking at a composite, the blown ion peel apply versus the hand prep. You can see there that we were able to achieve much higher forces of failure, and we were also able to reduce the variability, which is two things that, again, this whole webinar is talking about. We want to get a better product, get a better bond, and reduce variability. We'll turn it back over to Lucas to talk about this one as well.
Well, and this really fits in that same vein. I mean, here is an example of where we're taking, you know, composite samples, and we're just applying a range of surface preparation types, doing our absolute best job, and just comparing them. And so what we did is we did a solvent wipe only. We did a hand sand, solvent wipe followed by hand sand. We then did a grit blast, which is, you know, grit blast is like one of these legacy surface preparation methods for composites, which can actually do an incredible job, but is messy and has its own issues. And then following all of these on with air plasmas. And what we can really quickly see is, you know, us here in the lab doing our best job with a solvent wipe on these epoxy laminates, we're getting 100% less strength than we can get out of the air plasmas. And there's multiple reasons for that. I mean, one of them is we're manually solvent wiping. We simply just don't get the surface uniformity. We also don't remove as many contaminants as we can. The other thing is with the air plasma, we have extremely repeatable surface preparation, because we have a very controlled distance, we've got a very controlled speed, and we're chemically changing that surface. And all those things come together to just really improve the whole output. So Wilson, I think you can go ahead and take it away.
I apologize. I was muted and talking, and nobody could hear me. So my dogs were there, but no, they don't really.
Well, they could hear you. I know the dogs listen to you all the time, I'm sure.
Yeah, I know, but I don't think they really understand. So anyway, let's go move on with what will work for my operation. Real quick, we want to talk about our lab trials. As we've talked about a few times, every material is going to be slightly different. Every application is going to be slightly different. I get asked a lot, hey, can you give me the range? What's going to happen with polypropylene after I treat it? Well, there's too many variables for me to really give a good answer for that. We do have lab services in Menominee Falls where we can do both flame and plasma. We have the BTG system there to help us with contact angle. We also can do other types of testing along with that. We can overnight that material back to you, wrap it in certain ways, keep it clean as we possibly can. But we also do this on site, which is my preferred method, because we can treat something and then immediately go to whatever your next process step is, printing, coating, bonding, whatever. You can treat it and you can see immediately. Also, we carry around a BTG device on sales calls so that we can show immediately what the change was. Hey, we started at 80 degree contact angle, and after treatment we dropped down to 25 or 30 or whatever the number is. I'm just making those up as we go, but you can immediately see the impact of the plasma or the flame on the surface. All of these testing is free, and so just contact us and we'll be glad to do it for you. As we mentioned earlier, with plasma, we have to control distance and speed. So there's a lot of different ways to do that. We have stands and carts so that if you've got conveyor systems that you can just slide material up and measure your distances and be ready to go. There's indexing tables, as you see up top in the left-hand side. Many times plasma is very easy to integrate. The middle picture there, you're just treating a tube before it gets printed on. So all you're really doing is pointing the plasma in the right area. Very, very simple. It's a box application down there below. Again, you don't even have to do anything but measure the distance from the surface. But there are other applications when you're doing three-dimensional type products where you're going to need to use a robot. And so either one of those applications or integration techniques will work. Flame also has a couple of different. We again have all the guarding and everything that you need for the flame systems, whether it's a single or dual head system. The cage, as you see up there, will make sure, of course, that you keep employees out of there, because the flame is at about 1900 C, so it's obviously quite hot. Conveyor system there below, and you can see a wide burner there, as I mentioned before, that we can basically make one of any width that you want. Now, once you get above about 16 inches, you need to water cool the burner. So many times we'll break it up into 16-inch segments because it's a little easier to handle, a little less integration. But we also use robots with flame all the time. I'll turn it back over to Lucas.
Yeah, so process control, data-driven decisions. It's my favorite thing to talk about, believe it or not. So, we talked a lot really at the beginning about trying to use data to design and develop, scale the process, help solve a problem if something's going wrong. And there's just many, many, many examples of this that we've applied over the years. Whether I want to understand if, hey, I am going to abrade this part, do I want to use a Norton abrasive or a 3M Scotch-Brite, right? How do I make sure that the anti-clogging additive that they put in that paper is not embedding itself in my material and actually contaminating it by accident, right? If I spec in 120 grit paper versus a 220, does that even actually matter, right? I mean, or is it specified enough? Other examples of this are just looking at which solvent is better, or if I'm going to do a plasma operation, what's the speed and distance that's really going to give me the optimal optimal surface that I can then carry forward and launch very, very successfully. We find most bonding issues that we find are during launch, right? When we've introduced all these new variables that we weren't really accounting for in design, many times that have to do with kind of the supply chain we've set up. And 90% of them are surface driven. Usually it's not because in design or development we selected the wrong plasma unit or we did something like that. It's almost always because we just didn't have the technical objective communication and specification needed to scale that thing appropriately. And we weren't looking at it in the right spots. All right. So there's many, many examples of this that we could share. But these are just a couple examples, right? And when we get to this, with the kind of the state that really the best manufacturers out there in the world are at now, is where they've got active process control feedback loops where they can actively optimize what they're doing, right? We have the input of our material on the left-hand side of the chart that then goes through our particular system and gets processed, right, via flame or plasma. We then have an output that is actively measured in line with a digital solution. That data is then literally ported right back to the beginning of that process to actively optimize if needed, right? Not only just to say go, no go, but also say things like, hey, let's speed up the robot a little bit. We're getting great treatment here, right, in real time. So we get this contamination detection, we get these real-time metrics, we get predictive analytics for cleanliness that then flows into adhesion, and we get the trend analysis. So we don't get caught, you know, 6 weeks in or 6 months into a new product program with things falling apart or a scrap rate that's too high, and we can't answer that, you know, we can't answer that question. So with that, we're gonna play a video. You will not be able to hear me, and if you are on your computer, the sound will come through your computer speakers. If you are on the phone, you will not be able to hear the audio. So Mark's gonna go ahead and play a video where we show one of these tools in action.
Traditionally, we start with a handheld instrument, the Surface Analyst 5001. Okay, we have a measurement attachment here that allows us to initiate measurements right from the head. We've got the main body of the unit, and you can see very quickly that to be able to take measurements, say on this piece of aluminum, I can immediately initiate measurements right here from my right hand and immediately get results. 62. Now this piece of aluminum looks identical to the human eye, right? 86. It's highly variable. It's pretty dirty. All right? But I have, in fact, plasma treated a section of it over here. So if I go over here to an area that looks visually identical, what do I got? 46 degrees. $44 degrees. So a difference of almost 40 degrees from one corner to the other. All right, you couldn't know. We get 4.5 hours of battery life, lithium-ion battery. There's a cartridge in the back with HPLC water that allows us to take up to 1,000 inspections, trouble-free. I can even take measurements in any orientation, right? If I go vertically against this cabinet, I can build a droplet on that surface and return a number. I got an 86-degree contact angle right there on the side of the cabinet. So pretty straightforward. If I'm starting with a surface that in general, let's just say, let's get a measurement right here at this point. 78. I take a little piece of Scotch-Brite. I scuff sand this piece of aluminum fairly aggressively. Let's see what I get. 23-degree contact angle, right there in that spot. Obviously, it's visually different at this point, but I'm not always going to abrade a piece of aluminum either. But you can basically see the impact that you get right here on this surface and how this number allows you to clean to a quantifiable endpoint. Really great for setting standard specifications and bringing clean into the digital world.
I hope you guys liked my pre-quarantine hair. That was a new look for me. I thought that was pretty good. So I think we can move on to conclusions here. We're about 10 minutes before the end, right? So the
So Lucas and Wilson, thank you for really a great presentation. A lot of tremendous insights. We've got some questions we're going to get to. Before we do, let's just take a quick review of the highlights. Today you guys covered some really great insights on the concepts of reducing operational complexity, eliminating the human factor, and making data-driven decisions to improve both reliability and predictability. Also talked about the importance of surface preparation and how plasma and flame treating does offer numerous benefits, including reducing the variables associated with preparing surfaces for optimal bonding. So with that, we'll start answering some of your questions. If you have a more detailed question, feel free to reach out to Wilson or Lucas. Their contact information is on the screen. first question, Wilson, can you just talk about the general differences between corona, atmospheric, air plasma, and flame plasma?
Boy, that's a webinar in itself. They're all plasma. They're all ionized gas. They're just different forms of gas, and they do well in different things. Again, a flame gives you the advantage. So the best way to talk about them is probably in their applications. Flame is just better, as I mentioned before, on multidimensional surfaces. Less programming is involved. I've got more margin for error in my distance away from the surface. Plasma, blown arc, and blown ion, I need to be more cognizant of my distance and speed, but they also have perfect applications for them, whether you're going into small areas or wider areas to print. They just give you the advantage there. Corona is a different form of plasma where you're basically creating a capacitor on the surface of a film, and you're adding the corona, the ions are attacking either one or both sides of that film, and it's usually an in-roll, line-to-line, roll-to-roll process, so that you can go much wider. So corona gives you the advantage of being able to go to very wide widths more economically than you could do with plasma or flame. So again, they're all forms of plasma. They're all ionized gas, but they just have different setups that you could use for different applications. And so usually they're application specific on how much area you need to treat and how fast.
Thanks, Wilson. Lucas, this one might be for you. This person is asking, if we're speaking about optimizing adhesion, the adhesive is a very important component in the process. Do you have any insights on how to characterize the adhesives, surface tension, surface energy, cured and uncured, to find out if they are compatible with a particular well-characterized surface?
Yeah, so it is a good question. The adhesive is definitely obviously, it's one of our 3 key inputs, right? It's definitely an important part of it. There are ways that, depending on the adhesive type and its viscosity, there are different laboratory tests you can do to characterize its surface tension, really. I mean, if it's liquid, surface energy of a liquid is surface tension. There are a couple different tools for this. I mean, anything from like a real simple Denoy ring to a Wilhelmy balance to, there's basically different things you can use. Typically, when we're looking to select a particular adhesive, we're trying to look at a couple different factors. It's like, how easy is it to work with, right? Like, how am I going to dispense it? How am I going to store it? And from a functional perspective as to like whether or not it's going to do the job, like is it going to distribute the load that I want? Am I going to get the failure mode that I want? We're typically doing that through really just bonding up samples, not in shear, usually in like a double cantilever beam, for example, and pulling them apart and seeing kind of what happens. I mean, that's, unfortunately during the design and development phase, we can certainly down select our surface prep side really, really quickly using techniques like this, but in terms of what adhesive is going to be the best at the end of the day, that's stuff that we've got to we've got to do some functional testing on. So if you want to dig into that even farther, we could have a question with our lab team, and they would actually provide you some strategies on how to more quickly characterize an adhesive itself.
Thank you for that, Lucas. Wilson, this customer would like to know if plasma treatment can be used on all kinds of materials such as polypropylene, ABS, polycarbonate APS, and then there's a last one here. It's polypropylene, and then it's KENAF, KENAF, and this is a new material this customer has been using recently.
That one is a new material to me as well, but I would say that yes, plasma can be used on all the ones that you mentioned. There are a couple of materials that just do not take very well to plasma treat, at least open air plasma treatment like we do. Those would be fluoropolymers, really, PTFE, ETFE, FEP. Those are a little bit more challenging. Fluoropolymers have some interesting characteristics that make them less acceptable to the open air. You usually have to go to a chamber in order to get a good bond or printing or whatever on a fluoropolymer. There's also other materials used in thermoforming like POM that don't take treatment very well. But in general, most materials treat Generally, it's going back to how long does that treatment last and how much treatment you're able to get.
All right, Lucas, this is a question on the surface analyst. It looks like it reports back the contact angle. Is that enough information to see if the surface is improved in the right direction?
The two yeses. There are two yeses to that question. One, yes, it reports the contact angle of water. That's what it's measuring. And the second answer is yes, that is enough information. I can go into way more detail as to why, but just to keep it short and sweet, yes and yes.
No, that sounds good. Wilson, I'm not sure you covered some of this in the presentation, but if we want to revisit, we have a few questions related to the shelf life of something that's plasma treated and the timing of the secondary process. So if you can just revisit that topic for us.
Yeah, sure. Again, most materials, depending on how you store them, can last a decent amount of time. And I'm talking hours to days. For instance, the first question that talked about corona treating, when you corona treat something and then you roll it back up, you are preserving that surface energy for a much longer period of time because it's not in contact with the atmosphere at all. So in that case, the treatment can last days, weeks, months. But generally, when you're treating something with flame or plasma, you are going to bond or print on it. And so it's just always the best practice to do the next process step immediately. I know sometimes that's not possible. So if that isn't possible, then you need to take care in how the material is handled between that process step and the next one. I've had applications, for instance, an automotive windshield where it was being treated. And so they were asking the question, well, what do we do if we have a shift change or the line stops for a little bit? In that case, they just retreated the part because they were going to add the adhesive immediately, and with glass, over treatment was not an issue. But for best results, do it immediately. If you can't do it immediately, then we need to take care in how we handle that material going from one process step to the next.
Thanks, Wilson. All right, we're approaching our 1 hour time frame here. We'll try to get a couple more questions in. If we don't get to your questions, our experts will reach out to you after and make sure that you get the answers you need. Someone wants to know if they're working with carbon fibers, is flame the best option?
Both plasma and flame will work on carbon fiber or a composite. So carbon fiber, depending on the form that you want to do it in. If you're trying to treat the fiber itself, that is a challenge just because even though it's very strong in one direction, it's very brittle in another direction. So plasma can be difficult to treat. So we just have to be careful. If you're talking about materials made with carbon fiber, both plasma and flame work well.
All right, and one more question here. How does plasma ions typically compare to a liquid adhesive primer?
Well, they're both trying to do the same thing, and that's increase the surface energy. So again, with all the things that both Lucas and I have talked about, all of the techniques that have been used in the past, what you're trying to do is get a more uniform surface to do whatever your next process step is. The challenge, of course, is you can't, anytime you do something by hand, you're introducing variability that you don't need. We see this a lot in composites bonding because it's a very manual process, and generally their biggest complaint is they can get a good bond, but if one person will do it one way at 9 o'clock in the morning and different at 4 o'clock in the afternoon, if you have 100 different people doing the same process step, you're going to have 100 different ways of doing it. And so they're both trying to increase the surface energy. It's just which one you want to be more consistent.
Well, and I know we're at time, but I'd love to chime in on that a little bit. I mean, when you use a primer, you're literally consuming material while using it. You're literally painting the surface with a primer. That's expensive. It's environmentally not friendly. It's just not, if you can and people will slap primers on stuff to get stuff to stick just because it's not clean or not activated well. You know, one of the great advantages of surface treatments like a plasma treatment is that you get rid of that entire process.
All right. Thank you for that, Lucas. And thank you to our audience today. We will be sending a email tomorrow with a link that will get you the recording of this webinar and access to the presentation slides. Please let us know any thoughts you have on the webinar by reaching out to Wilson or Lucas. We appreciate your comments and insights. If you have ideas for future topics on surface preparation and surface diagnostics and best practices, please let us know as well. Thank you again for your time today, and that will conclude today's webinar.
Thank you.